Okay. So today in the lecture we will cover an algorithm which basically, so given an Euler graph, so basically, hello, am I audible? Hello.
Yes, sir.
Okay. So basically today's the algorithm is basically help us to find out an Euler circuit in a directed graph. So let's study the algorithm. So basically you are given this, you are given a connected directed graph or digraph G, where each vertex has equal in degree and out degree. So D plus U means in degree of U equal to out degree of U. Now output is a directed Euler trail. So basically you are given a connected directed graph where every vertex has uh, so for every vertex U, the in degree of U equal to out degree of U, and your task is to find a directed Euler trail. So this is the algorithm. So I don't go through these steps, rather I will explain this with an example. So this is a directed graph and I take any arbitrary vertex V. So I can take any one of them, but I take this vertex as V. And my task is to found and for each vertex, if you notice that in degree equal to out degree. Say for example, for this vertex, in degree is 1, out degree is 1. For this vertex, in degree is 2. This and out degree is also 2. Okay. For this vertex also, in degree equal to 2 and out degree equal to 2. So if the graph has this property, then we can found an Euler tree. Okay. The algorithm is as follows. Okay, this graph is given. The first task is to reverse the edges of the graph. Okay, so we reverse the edges. So if you look into this is the original graph. Okay, so if you see this is the direction, and in the next slide this is reversing the edges. So it will take order of v plus e time, right? And then what we will do, we will run a DFS on it and find a DFS tree. So on this reverse graph G prime, we run a DFS from V. So we go there, and from there and we go like this. The red edges are the DFS tree edges. From there is so if I go by this, I will already visited this, so I can't go. So I need to backtrack and I have to go here. So this red edges give me the DFS tree T prime consisting of, so DFS tree T prime gives the red edges. So this is the DFS tree edges. Now we again reverse all the edges to get back the original graph. But the only thing we need to keep in mind, these edges, these red edges need to be remembered in the data structure. Okay, so this was the edges. So these red edges are converted to green edges. Okay, so basically this is my original graph. This was the green edges and other are the blue edges. Okay, now I will start my Euler circuit transaction. So basically what happened so far, it was the original graph, order of v plus e time needed to reverse this graph, again order of v plus e time needed to DFS. Again if I revert it back, order of v plus e. So basically order of 3 into v plus e time, we get these blue edges and green edges. Now I have to find out the Euler circuit. So what I do, from any given vertex, you see here I write use blue edges for leaving a vertex always. If there is no blue edges left for leaving some vertex, then only you use the green edges. That is the algorithm. So from V I start. So I go, this is my first edge I visited. Then here I have one green edge, one blue edge, but I will stick to blue edges. So use blue edges as long as for leaving a vertex. So this must be my second edge. Then here when I come in this vertex, I have one green edge, one blue edge. So again I go by blue edge. 3. Then from here I have this green and blue edge. Again I go by blue edge. 4. From here I come back here. 5. Then I go back here. 6. So far we use only blue edge, but here when we come back, we see that there is no blue edges left, which is already visited, because we have to visit every edge exactly once. So we go by this green edge now. Again when we come back, again I will go by the blue edge. So this edge is empty, so this is my 8th edge. From here I have one green edge, another blue edge. So again I go by this blue edge, 9th edge. But when I came here, I see that there is no blue edge which is not visited. So this edge already visited. So I have to go by green edge. Now I go by 11, 12, 13, 14 and 15. So I start from V, I come back to V. So I get the Euler circuit. Okay. So the good part of this algorithm is, so, and if you do this, it will take again order of V plus. So it is order of 4 into V plus E algorithm. That means order of V plus E time. Now, okay, this is the application. Okay. So if we go by this algorithm, we find that why this algorithm works. Let's try to figure out informally why this algorithm actually works. So basically, initially this was my graph. Now if I do so let's go with the algorithm. So in step 1 was, your input is G. Now you create a graph G prime by reversing the edges. Okay, digraph obtained from G by reversing the edges. Then you do a DFS on G prime to construct T prime consisting of paths from S to V, G prime minus S. So now you reverse the edge and you do a DFS. Now in G prime, what DFS tells you, from V, how you can reach all other vertices from V. Okay, so this rare edges actually signifies, given a vertex V, how you can reach all other vertices. Now in the next step, when we reverse them, what these green edges signify? These green edges signify that from different vertex, at any vertex, from any vertex, how can you come back to V? Okay. So basically in Euler's circuit, there are few edges through which you go to other vertices, and there should be few edges through which you come back to V. This green edges basically gives you the edges through which you can come back to V. That is why we use the blue edges first. So we go by blue edges, we don't touch the green edges. We go by these blue edges, and so you go by these blue edges, and when you are not left with any blue edges, you go by the green edges, because these green edges will tell that you will come back to V. Okay, so that is how this algorithm works. So first you go first edge, then second edge, third, then fourth, fifth, you go to sixth. Now you don't have any other option. So you take the 7th edge and you come back to V. Okay. Now in Euler circuit, you know that the same vertex can be visible in multiple times, but edges will be traversed only once. Now from here you start the next thing, 8, 9, 10. Then you have no other option. So all the blue edges are covered. Now you use the green edges to come back to V. This DFS, reversing the edges of the graph and then do a DFS and again reverse it back, gives you the edges through which you come back to V. Okay, so that is the algorithm. Now we see that an application of this concept. Okay, so the problem is as follows. So application of Euler diagram, this is called de Bruijn cycle. So basically the problem is as follows. So we know that given n bit, we can create 2 to the n binary strings. That we know. If n is 3, we have to cube 8 different combinations. Now the question is there a cyclic arrangement of these 2 to the n binary digits such that the 2 to the n strings of n consecutive binary digits are all distinct? So what does that mean? Suppose somebody asks you, okay, you are given n and you have to store 2 to the n values. So what is the memory required to store all these values? You have, for each string you have n digits and we have 2 to the n such combinations. So n into 2 to the n is the total space complexity. The problem de Bruijn cycle gives that instead of using this n into 2 to the n space, you can store this information in using only 2 to the n space. Okay, and for n equal to 3, this is the solution. So that means using 8 bits, actually you can store all these 8 different combinations. You can check like 0 0 0. Okay, so I marked 0 0 0. It is green. Then next one is 0 0 1. Okay, so 0 0 1 is also there. Then 0 1 0. Okay. 0 1 0 के बाद it is 1 0 1. Then 1 0 1 के बाद 0 1 1. Okay, so it is 0 1 1. And 0 1 के बाद 1 1 1. And it is a cyclic arrangement. So 0 1 1 के बाद 1 1 1, then it is 1 1 here, 1 1 here and 0 here. So 1 1 0. So this is my 1 1 0, and then single 1 here, 1 0 0. This is 1 and these 2 zeros. So 1 0 0. I see that all of them are covered. So if I place these numbers in a cycle, we can see that all these 8 combinations are covered. The question is, how can I create such a circular arrangement? The benefit of learning this algorithm is, the Bruijn cycle algorithm is basically, you are given, so basically you are trying to store 2 to the n different bit combination, not in n into 2 to the n space, but using only 2 to the n spaces. Okay, so to design such an circular arrangement, de Bruijn has used Euler digraph to create such a circular arrangement. Now we will study how De Bruijn has created such an arrangement. So your input is say n equal to 3 and your output is this circular arrangement. Okay, so anyways, these are the things that is written. So how to construct De Bruijn cycle? So De Bruijn cycle जो graph है, so n is the number of, so n is number of bits. If n is 3, then it is D3. Okay, for D3 we will have a graph. We will show how De Bruijn graph looks like. Okay. Now यहाँ पे okay, so define it. So when you are creating a graph, you know that you have to create few vertices, you have to create few directed edges. So if there are n, if n is 3, then what De Bruijn says that define a graph D3 whose vertices are the binary n minus 1 tuples. That means binary 2 tuples. So if n is 3, the edges are like this 0. So n is 3, so आपको 2 tuple बनाना है. 2 tuple क्या क्या होगा? 0 0 0 1 1 0 and 1 1. 0 0 0 1 1 0 and 1 1. That is the first task you will do. Next you have to create the edges. So he says put an edge from vertex A to vertex B if last n minus 2 entries of A is equal to the first n minus 2 entries of B. Okay, so here n is 3, so n minus 2 is, that means 1. So 0 0 and 0 1. Okay, so iska last entry has 0, iska first entry has 0. So I will put an edge here. Okay, this is 0. Again we come back to this. So iska first bit has 0, iska last bit has 0. So there is a self loop. For 1 1 there is a self loop. For 1 0 to 0 1, from 1 0 to 0 1 there is a edge. Why? Because iska last bit has 0, iska first bit has 0. So there is an edge. Similarly from 0 1 to 1 0 another edge, because 0 1 का last bit है 1 and 1 0 का first bit है 1. Similarly 1 1 and 1 0, last bit है इसका 1, इसका first bit है 1. So there is a edge. Not only that, I have to, we have to create it is a weighted graph. So label the edge with the last entry of B. Okay, so basically what are the steps? There are basically three steps: creating the vertex, creating the edges, and assigning the weight to the edges. So how do we create edge? If n is 3, then n minus 1 is 2. So I will create all 2 to the n, or sorry, all 2 to the n minus 1 combination as my vertex. Okay, so if n is 3, we have 2 to the n minus 1, that is 2 square. 4 vertices are there, which are labeled as 0 0 0 1 1 0 and 1 1. Second stage is creating edges. We put an edge from vertex A to vertex B if the last n minus 2 entries of A equal to the first n minus 2 entries of the B. Not only that, we will give a label to it. The label is इसका last n minus 2 entries equal to its first n minus 2 entries. जो remaining entry बाकी है वो इसका लेवल होगा. We'll see an example. So suppose 0 0 0 1. So इसका last bit है 0, इसका first bit है 0. So we have put an edge. And what will be the edge? Limit is 1, because 0 0 to 0 1 में this is A, this is B. B का जो last bit है that is 1. So that is why it is 1. So for example 0 1 to 1 1. इसका last bit है 1, इसका first bit है 1. So there is an edge. But ये B, if it is A, it is B. The last bit is also 1. So its level is 1. तो B का जो last bit होगा, A to B edge में B का जो last bit होगा, जैसे 1 1 to 1 0. So B का last bit है 0, so 0 will be its edge. So 1 0 to 0 1, there is an edge, but since B is 0 1, so B ka last bit है 1, so this will be 1. Similarly 0 1 to 1 0, so इसका last bit है 1, इसका first bit है 1, B का first bit है 1, so there is an edge between them, and this is B. 1 0 is my B, so इसका जो last bit होगा, that is 0, that will be the edge. So this is called D3, and this is called a De Bruijn graph. Now that is how we create the graph. Okay. Then we have to prove this. Dn is Eulerian, and we have to prove that if I create an Euler circuit of this graph, it will indeed gives me this circular arrangement which we are interested in. Okay. So this D3, मैं D4 के लिए भी एक दिखा रहा हूं आप लोगों को. D4 के लिए n equal to 4. So for n equal to 3, 2 cube, 8 vertices are there. 0 0 0 0 0 1 0 1 0. Okay, then 0 1 1, then 1 0 0 1 0 1 1 1 0 1 1 1. And यहाँ पे क्या होगा? यहाँ पे first n minus 2 entries, that is n minus 2 is 2 here. This is 0 0. Sorry, last n minus 2 entries. So इसका last n minus 2 entries 0 1 is the first n minus 2 entries of this 0 1. So there is an edge between them, and इसका लेवल क्या होगा? इसका लास्ट बिट, b का लास्ट बिट 1. So 1 is this. कॉमा के बाद जो नंबर है उसको फॉर द टाइमिंग भूल जा. फॉर द टाइमिंग मतलब इट्स नॉट नीडेड टू बी कांस्टेंट. Say for example 0 1 1 and 1 1 1. So last two bits is 1 1 1 1. यहाँ पे first two bits is 1 1. So there is an edge between them, and the label will be 1. That is, if it is A, it is B. So B का जो last bit होगा, that will be its edge value. Now what this number says, this 1 2 3 4 up to. So this numbers basically shows that the Euler cycle. So given this graph, if you find an Euler circuit in this graph, then that Euler circuit will give you the De Bruijn cycle. So basically जैसे for n equal to 3, this 0 0 0 1 0 1 1 1, this is my circular arrangement. So how do I get it? So for this graph I will do a traversal. So 0 0, okay, then okay, I don't know from where I have started here, so might be I think I start from here. So I go by 0, then this 0, then this 0, 3 zeros, then 1, then 0, then 1, then 1, sorry, then 1, and then last one. So basically, so I first traverse this, so I will comma 1. I secondly traverse this, third I traverse this, fourth I traverse this, fifth I traverse this, sixth I come back to here, seventh this, and this is the 8th one. So that is how I get. So, and how do I traverse this? I know that, so we have discussed the last algorithm where we know how to find this Euler circuit. So edge level, so there are 8 edges here. There are 8 such edges. So, and so this is the circular arrangement I got. Similarly, here also de Bruijn cycle is 0 1 0 0 1 1. So it is like I first find there 0, then 1. Sorry, this is the first edge, this is the second edge, then this is the third edge, this is the fourth edge, then fifth edge, then you go by the sixth edge, seventh edge, eighth edge, 9th, 10th, 11th, 12th, 13, 14, 15 and 16. So you start from here, you end up here. And all the edge levels, so this is 0, then followed by 1, so 0, 1, then coming 0, 0, so 0, 1, then this is 0, this is 0, 0, 1, 0, 0, then this is 1. So that is how we create this de Bruijn cycle. Okay. So that is the algorithm. That is how you find the de Bruijn cycle for some n equal to 4 or 5 such that. Okay. The question is, there are two things we have to prove. The first thing we have to prove that the de Bruijn graph is an Euler graph. Okay. And that is very simple to prove. Every vertex has out degree 2 and every vertex has in degree 2. Why that is so? Every vertex has out degree 2 because we can put a 0 or a 1 at the end of the vertex level to get the successor vertex. Okay. So take any one vertex. Suppose you take 0 0 1. Its out degree is 2. So 0 0 1 के बाद अगर मैं एक 0 बैठाता हूं, so basically how these edges are being created, the last 2 bits equal to the first 2 bits. So 0 1 यहाँ पे और यहाँ पे भी 0 1 है, तो we will connect them. Now I can put a 1 over here or a 0 over here. If I put a 1 over here, it will go to 0 0 1, it will go to 0 1 1. If I put a 0 over here, because there are two only possibilities, 0 and 1 bits, there is no other possibilities. So 0 1 के बाद अगर मैं यहाँ पे 0 बैठाता हूँ, तो it will come to 0 1 0. So that is why for each vertex, out degree is 2, because the last two bits should be equal to the first 2 bits. Now, an edge level is basically the last bit of this. So last bit will be either 0 or 1. If it is 1, then from 0 0 1 I will go to 0 1 1. If the last bit is 0, I will go from 0 0 1 to 0 1 0. Okay. So that is why the out degree is 1, out degree is 2. Similarly, every vertex has in degree 2. Because if we can put a 0 or a 1 on the front of a vertex level, we can get the predecessor vertex. So basically same. Suppose 0 0 1. इसके पीछे अगर मैं एक 0 लगा दूं, तो 0 0 0 will be previous vertex. Again इसके पीछे अगर मैं एक 1 लगा दूं तो भी हो सकेगा. 1 0 0 से भी मैं आ रहा हूं ये 0 0 1. राइट. सो हर एक वर्टेक्स का, सो इट इज 0 0 1. इसके पीछे मैं 0 लगा सकता हूं या 1 लगा सकता हूं. अगर मैं 0 लगा देता हूं, इसका मतलब यह है कि दिस so from 0 0 0 you go to 0 0 1, right? So इसका लास्ट 2 बिट इक्वल टू इसका फर्स्ट 2 बिट. सो इसका एज लेवल क्या होगा? 1 होगा. तो कब इसका एज लेवल 0 हो सकता है? इसका नहीं, 0 होने की जरूरत भी नहीं है. लाइक यहाँ पे जैसे दोनों का ही बिट 1 है. सो basically what they write, every vertex has in degree 2 because we want to put a 0 or a 1 on the front of the vertex level to get the predecessor vertex. अगर मैं यहाँ पे 0 बैठा दूं, so 0 0 0 is my previous vertex. अगर मैं यहाँ पे 1 बैठा दूं, 1 0 0 is my previous vertex. Okay. So हर एक vertex का in degree भी true है. So since every vertex has in degree 2 and out degree 2, and also since Dn is a strongly connected graph, because we can reach the vertex B. So every vertex has n minus 1 bits. They are namely B1 through Bn minus 1. So Dn is strongly connected. How do we prove that? We can reach the vertex B from any other vertex by successively following the edges B1 through Bn minus 1. Okay, try to understand this point. Suppose 0 1 1. Okay, किसी भी नोड से अगर मैं 0 1 1 ट्रैवर्स करूं, then I will reach this vertex. Why? Dn is strongly connected, that every vertex has some bit combination like 0 1 1. Now due to construction I know that if I from any vertex, if I read the vertex level 0 1 1, I will reach to 0 1 1. Take any vertex. Suppose you take 0 0 0. So from here you follow 0 1 1. So this is 0, then 1, then 1. You reach here. अच्छा 1 0 0 को लेते हैं. यहाँ से 0 1 1 में स्टडी कर रहा हूँ. This is 0, this is 1, this is 1. अच्छा 0 1 0 से मैं स्टडी करता हूँ. This is 0, this is 1, this is 1. 1 0 1 से मैं 0 1 1 जा रहा हूँ. This is 0, this is 1, this is 1. 1 1 0 से, so this is 0, this is 1, this is 1. 1 1 1 से भी, this is 0, this is 1 and this is 1. So every vertex is reachable from every other vertex through these bit combinations. Okay, so that is why it is strongly connected also. So every vertex has in degree 2, out degree 2, and it is strongly connected. So Dn is Eulerian. So the first thing we have proven that it is Eulerian. Since it is Eulerian, we know that it has a Euler circuit, and that algorithm gives me that Euler circuit. But the thing that remains to prove is this, that the edge levels of the edges in the Eulerian circuit of Dn indeed form a cyclic arrangement in which all the 2 to the n consecutive segments of length n are distinct. Okay, so this thing we need to prove. So how do you prove it? Okay. So first again I read the theorem. The edge levels of the edges in any Eulerian circuit of Dn form a cyclic arrangement in which the 2 to the n consecutive segments of length n are distinct. Okay, that is something we need to prove. The first observation in this graph is, every vertex has, so if n is 4, then every vertex has n minus 1 bit combinations and every vertex is unique. Okay, so all 2 to the n minus 1 unique vertex combinations are there. That is the first observation. Okay, so if n is 4, we know that if n equal to 3, all the vertex combinations starting from 0 0 0 to 1 1 1, every bit combination is there for each of the vertices. So every vertex level is distinct. That is clear to us. Okay, that is the first observation. The second observation is, suppose we take any vertex. Suppose I take 1 0 1. Okay, now when I reach to 1 0 1 from any vertex, when I reach to 1 0 1, I know that. So when I reach to 1 0 1, the last vertex, the last number is 1. The last bit is 1. That means इसके जितने भी incoming edges होंगे, उसका लेवल 1 ही होगा. So 1 0 1 में जो भी incoming edges है, ये edge है, इसका भी लेवल 1 होगा, ये भी incoming edge है, इसका भी लेवल 1 होगा. Okay, so last bit of any vertex बेसिकली टेल्स यू कि इसके प्रीवियस एजेस का, इसका इनकमिंग एजेस का लेवल क्या होगा. सो लेट्स सी विद Eulerian circuit of Dn. This is basically the circular arrangement we are talking of. Arrival at a vertex A1 through an minus 1, there are n minus 1 bits, must be along an edge labeled an minus 1. So last bit an minus 1. So any arrival to this vertex A is through the edge whose level is an minus 1. Why that is so? Because that is clear from our construction. Because the level of an edge entering A agrees with the last entry of the name of the vertex. Okay. So basically, given any vertex, the last bit basically gives you the edge level of the incoming edges. Why? Because that is our construction. Now, since we delete the front and shift the rest to obtain the rest of the name at the head, the successive earlier levels looking backward must have been an minus 2 and a1 in order. So what it tells, so when we go to 101, 1 is the last vertex. So incoming edges both have degree, so both have 1 1. Now what about this 0? 1 के characteristics मुझे पता चला. If last bit is 1, if last bit was 1, इसका मीनिंग है कि इसके प्रीवियस जो दो वर्टेक्स है उससे जब आया है उसका एज लेवल 1 होगा. नाउ ये प्रीवियस दो वर्टेक्स का कैरेक्टरिस्टिक्स क्या है? व्हाई आई हैव ए एज फ्रॉम हियर टू हियर? द रीजन इज द फर्स्ट टू बिट्स 0 1 is equal to the last two bits 1 0. Okay, now so first two bits of it, and not only that, we should go back here. So the last two bits of this 1 0, which is equal to its first two bits. Similarly, इसका भी जो last two bits